Welcome to the Fundamentals Lecture for CHEM118 Experiment 1. This week we'll be exploring protecting group chemistry. So we'll start by discussing a generic example of exactly what a protecting group is and how it works. Then we'll get a little refresher on how SN2 reactions work, because we're going to conduct a Williamson ether synthesis in laboratory to apply a protecting group to a very specific molecule to achieve a very specific goal. We'll also have a little refresher on Proton Nmr spectroscopy, because we'll be using this technique as an identification tool. So the question for the week is this: can we selectively protect one of two hydroxyls on a vanillyl alcohol molecule? You'll get more familiar with what vanillyl alcohol is and exactly which protecting groups and hydroxyls I'm talking about in recitation. But for today, let's keep our sights focused firmly on learning about protecting groups in general. So let's start with a generic molecule. Call it whatever you like. I think it looks a little bit like Mickey Mouse. Now I drew this molecule with a sort of an inert body and two reactive groups, a more reactive dark red group and a less reactive sort of pinkish colored group here. And I want to attach to them another type of functional group or molecule, let's say this blue molecule. Well, there are three possible permutations of that reaction. One in which I have both sites modified, one in which I have only the more reactive site modified, and one in which I have only the less reactive site modified. So as a chemist, how might I accomplish each of these three goals? Well, let's consider the first. How might we modify both of those sites? Well, in this case, it's a fairly simple task. We can simply use a large excess of the reagent to be sure there's enough there to completely saturate any site that will react with it. In doing so, we can accomplish our goal of modifying both of the reactive sites. Now let's think about how to modify just the more reactive site. We can usually get away with using a little trick that we sometimes call stoichiometric control of the reaction. Basically what we're doing here is using just a very limited amount of the reagent that we want to attach. And in doing so, we expect that we'll make more of the product with the more reactive site functionalized, simply because of statistics. If it reacts faster, we should get more of it. So at this point, we've already come up with strategies that will allow us to achieve two of the three possible products. Using a large excess of the reagent will give us one modified at both sites. Using a very large deficiency or very small amount of the material that we're going to attach will give us a product which will be modified at the more reactive site. But it's a little bit more tricky to get that adduct onto the less reactive site without it reacting with the more reactive site. So we haven't yet come up with a strategy that will allow us to make that connection and produce that specific product. Sometimes when faced with a challenge like this, a strategy known as protecting groups is employed. And in a strategy involving protecting groups, we have to introduce a couple of new reagents. First, what we need to do to produce this product is we need to bring in a reagent which either will only react with the more reactive group or reacts much more favorably with it. We also are going to need a reagent which can then remove that group later without affecting the chemistry that we've accomplished that we want to do. If we can find reagents that can do this, we can accomplish our goal using a protecting group synthesis strategy. For example, we simply cover the more reactive site with some other type of functional group which makes it inert to the chemical conditions of the reaction we want to accomplish. We then run the reaction that we want to accomplish, thereby functionalizing the less reactive site. And finally, we remove that protecting group from the more reactive site, exposing it again once the addition or the reaction that we'd like to conduct is complete. So we have a situation where we're going through three steps to accomplish what we can otherwise do in one in the other two examples. First, we add that protecting group to the more reactive site. Second, we conduct the chemistry we want on the less reactive site. Third, we remove the protecting group from that more reactive site, and we have completed our synthetic strategy. This week we'll be using a reaction that involves the deprotonation of an alcohol to initiate a substitution reaction. Now, alcohols can be a little bit tough to deprotonate sometimes, depending on exactly what type of alcohol we're using. So consider just a typical aliphatic alcohol like T-butoxide. This can be deprotonated by a sufficiently strong base, but what's sufficiently strong here? Well, in the case of T-butanol, we have an aliphatic alcohol whose pKa is about 16, so it's an extremely weak acid. But we have some pretty basic stuff in the lab. For example, sodium hydride, in which we use this as a source of hydride ion, which is the conjugate base of hydrogen gas. So we can expect a fairly rapid proton transfer reaction to take place in this situation. And in doing so, it generates a hydrogen as a byproduct. So now we've created an alkoxide and a hydrogen gas molecule whose pKa is 35. So this is a very favorable reaction already. But what really seals the deal is that hydrogen can then effervesce from this mixture, and in doing so make the process completely irreversible. So sodium hydride is a great way, or sodium metal for that matter, is a great way to produce these alkoxide ions, but of course these are extremely reactive and potentially dangerous reagents. So let's watch an SN2 mechanism, since we know that the Williamson ether is an SN2. We'll take that alkoxide that we've generated and give it some kind of an alkyl halide substrate to attack. In this case, I'm going to go with methyl chloride for my example. So the alkoxide will attack the central carbon, the only carbon on the methyl chloride, inducing the chloride to leave. And in doing so, we go through an intermediate which requires inversion. Of course, in the case of methyl chloride, this really doesn't matter because there's no stereochemistry to invert. But at the end of the reaction, what we've accomplished is to create an ether and a halide ion as a byproduct. You'll probably recall from when you reviewed the Williamson ether synthesis in the first semester of organic chemistry that unless the ether is perfectly symmetrical, there are two potential sets of reagents which can be used to create the product that you want. Take the example of di-T-butyl ether here. Because it has exactly the same groups on both sides, there's only one set of reagents that might be used in a Williamson ether synthesis. Now in the case of di-T-butyl ether, this is unfortunate, because that means you would have to use a tertiary substrate, and we really can't make this very easily using this kind of a synthesis. However, T-butyl methyl ether, as we just saw, can be made. There are two potential sets of alcohol and alkyl halide. The first is T-butanol and methyl chloride, which is a primary, which would work. The second would be methanol and T-butyl chloride, but if we consider this reaction pair, it's clear that it will not work because the T-butyl chloride is tertiary and has a very obstructed electrophilic site. In situations like ethyl methyl ether, we actually could use either one because in this case we have either ethanol and methyl chloride, which would be a methyl substrate, or we could use methanol and ethyl chloride, which involves a primary substrate. So there are going to be situations in a Williamson ether in which we could consider creating the product that we want two different ways. One very commonly used protecting group when it comes to alcohols in organic chemistry is in fact an ether. Benzyl and allyl ethers are favorite protecting groups of organic chemists because they can be fairly easily attached to an alcohol group using an SN2 synthesis strategy. After that, they can be easily removed under a number of different conditions, some oxidizing, some reducing, some acidic, some basic. So we can choose the removal conditions which are most appropriate for whatever type of chemistry we've affected elsewhere on the molecule. We obviously don't want to hurt what we've done to the molecule while it was protected. This is why you'll often see benzyl and allyl ethers used in this way. In the research labs of Professor Holman here at Georgetown University, compounds known as cryptophanes are being synthesized. And cryptophanes are these large organic molecules. They look like this, and they can be created to encapsulate very specific atoms, ions, or even small molecules, acting as a sort of a selective sponge to draw a desired substance out of a mixture. It's some fascinating research, and creating these tryptophanes is not a trivial matter. In order to make them, Professor Holman starts with this molecule here, vanillyl alcohol. But you notice vanillyl alcohol contains 2 hydroxyl groups, and in his first synthetic step, he wants to create a molecule in which he has only reacted it at one of those hydroxyl sites. Notice here that the phenolic OH is still intact in this end cap of the tryptophane that he's creating. The problem is that he can't make the reaction work when the other hydroxyl is still there. So it's necessary, first, for Professor Holman to cover the hydroxyl that he doesn't want reacting when he creates his end caps. In doing so, he's placed a protecting group on that phenolic hydroxyl. He can then conduct his chemistry and remove the protecting group to get where he needs to be. Of course, all this requires that there be an allyl ether created only at the phenolic OH and not at the benzylic OH of vanillyl alcohol. This is going to be our question for the week. How can we get this done? Step 1 of his protecting group strategy is going to be up to us. Now let's take a little bit of time and refresh our memories on how Proton Nmr works so that we can use this technique as an identification tool in the lab. Let's begin our discussion of NMR with the phenomenon of Zeeman splitting. All spin 1/2 nuclei have a magnetic dipole, and spin 1/2 is just a fancy way of saying that the nucleus has 2 different potential magnetic states. This is true of protons, carbon-13, fluorine-19, phosphorus-31, and many, many other isotopes. In fact, practically every commonly encountered element has at least one isotope that is spin 1/2. Now, when we place a sample of these atoms that are spin 1/2 in an environment where there is no magnetic field, their magnetic dipoles simply align randomly. However, when we introduce a magnetic field to this, what we see is that they align themselves with that field in very special ways, either perfectly parallel to the field in what's known as the alpha spin state, or anti-parallel to the field, which is known as the beta spin state. What's really important about these 2 different states, alpha and beta, is that there's a difference in energy between them. One is not as stable as the other. So we call this the Zeeman splitting energy. It can be calculated using a series of constants, including the gyromagnetic ratio, which is an intrinsic property of the nucleus, the same for all protons. Planck's constant, which is, as the name implies, constant. The strength of the field that is causing them to align in the way that they are. And sometimes you'll see a 2 pi term in there to convert from radians to degrees. Now, 3 of these 4 terms are constants, which means that if we eliminate them from the equation, we still have a proportionality. We can say that the Zeeman splitting energy is proportional to the field that is being experienced by that nucleus. This is a key fundamental property that we need to remember it to explain how NMR works. So because we have our equation for Zeeman splitting, and we can simplify it to this proportionality, we can plot the difference in energy between the alpha and beta spin states, and we get something that looks like what's on your screen now. With the unaligned spins all the way down here where there's no field applied whatsoever, and of course, as we continue to increase the strength of the applied field, we simply increase the energy gap between those 2 states. The alpha becoming ever more stable, the beta becoming ever less stable as we increase the field strength. It's the energy difference, the Zeeman splitting, that we're really measuring during what's known as a continuous wave NMR experiment. A continuous wave NMR is not really used much anymore, but it's a much simpler technique to understand, so we're going to start there. In a continuous wave NMR experiment, we have a radio transmitter on one side of the sample and a detector on the other. If we place a sample inside of a magnetic field between the two, and that sample contains spin 1/2 nuclei, they will align themselves in parallel or anti-parallel states according to their Zeeman splitting energy. Now, let's produce a continuous wave of a single radio frequency. At the moment, that radio frequency is getting through to the detector. So if I were to plot the energy or the intensity of the radio frequency that's being viewed at the detector, right now it would be fairly strong. In other words, there's no absorption. So as I continue to increase the strength of the applied magnetic field up to the Zeeman splitting energy, I see nothing. The radio frequency wave is still getting through. But when the field is such that Zeeman splitting is exactly equal to the energy carried by the radio wave, a transition occurs, and the radio wave is absorbed as those nuclei flip from the lower energy alpha spin state to the higher energy beta spin state. And this registers as an absorption. As I continue to increase the strength of the field, I go beyond the Zeeman splitting. I go beyond the energy of the radio wave, and we go back to the case where there is no absorption. This is the source of a peak in an NMR spectrum, at least in the original version of NMR. Now, later on in the lab, we'll be working with some more sophisticated NMR techniques, and we'll go over those when we're in lab as we're refluxing our reaction mixtures this week. So if you're following along, we have a technique that allows us to detect the transition of spin 1/2 nuclei from the alpha to beta spin state by scanning through magnetic field strengths as we irradiate it with a constant wave of radio frequency radiation. That difference in energy being proportional to the magnetic field strength allows us to do this. So if I have a collection of protons and I increase the field to which they're exposed, I can get an absorption of radio frequency. But there's one question left unanswered here. That is, if this is true, then why is this technique good for anything but detecting the presence of protons? If all protons have the same gyromagnetic ratio, and Planck's constant is indeed constant, then why is it that we get multiple peaks in an NMR spectrum? What is it that causes some protons to absorb or resonate at different magnetic field strengths? Well, the answer is that protons are not isolated in a vacuum, as in our example here. Protons in chemistry are on molecules, and those molecules have electron clouds and other elements and atoms bonded within them that manipulate or squish those electron clouds around. So if we consider the effect of that on the magnetic field, we have to remember that electron clouds have this interesting ability to shield the nuclei that they surround from applied magnetic fields that are external. So now our magnetic field term is not simply the applied field, but the applied field modified by some kind of shielding. So in my example here, I have ethyl chloride, in which there are two different kinds of proton nuclei there. Right? These two hydrogen nuclei are on a carbon containing a chlorine or on the carbon that's one bond away from the chlorine. And that electronegative chlorine causes a more de-shielding effect on hydrogens that are closer to it. In other words, those protons that are closest to the chlorine will experience a greater magnetic field at that nucleus than will the others. And the result of this means that they will resonate at a lower applied field. Now we have a technique that should give us two different peaks for a molecule containing two different kinds of hydrogen. But there's one more property we have to consider when it comes to molecules like ethyl chloride. When we look at their NMR spectra, we actually see something much more complicated than just two peaks. So let's think about why that is. Well, here's our ethyl chloride molecule, and here is one set of hydrogens. These two are chemically the same, but they have three neighbors that are not the same. And when we look at their NMR spectrum, we don't see a single peak for them. Instead, we see 4 smaller lobes. The reason behind this is that the neighbors, remember, are spin 1/2 nuclei, and they actually create small magnetic fields of their own. And those fields affect the field experienced by their neighbors. If they're all spin up, they will contribute to the field. We can have the situation where 2 of them are spin up and 1 of them is spin down. There are actually 3 different permutations of this. Similarly, there are 3 permutations where the neighboring hydrogens are 2 down, 1 up. And finally, there's a fourth situation in which we have all of them spin down. Now we can see why we get this kind of a peak when we expected to see only 1 resonance for those red hydrogens. And similarly, those red hydrogens will affect the absorption characteristics of the blue. When we look at the peak that we assign to the methyl group, we see that it's actually a triplet. This because there's 1 permutation of neighbors where they are both in their alpha spin state, 2 permutations where we have alpha and beta, or up and down, and 1 permutation in which they are both antiparallel. This is the source of the multiplicity that we see in NMR spectra, and also the source of what we like to call the n+1 rule. The n+1 rule simply states that you have n+1 lobes in the multiplet for protons that have n number of neighbors. This works very well when we have bonds with free rotation and all of the non-equivalent protons are coupled to one another with similar coupling constants. But as we'll see later, this isn't always the case. Typically, however, it is the case, and we see very specific types of multiplets very often in NMR, such as doublets, triplets, quartets, quintets, sextets, and so on. Once we reach the sextet designation, we sometimes simply call them multiplets and abandon naming them by their specific number of lobes within the multiplet, but sometimes you'll see them go much farther than this. There's a pattern of intensities within these multiplets that can be predicted using a geometric mnemonic known as Pascal's triangle. Pascal's triangle, again, works really well when we have equivalent coupled neighbors and we generate these very common multiplets. So let's take a look at a couple of NMR spectra for 2 similar molecules and see how we can use these NMR spectra to tell them apart. We'll start with 2-chloropropane, which has an NMR spectrum that looks something like this. Notice that there are 2 different kinds of protons. I've labeled one type of proton in blue and 1 type of proton in red. Now take a look at that red multiplet there. There are actually going to be 7 lobes because there are 6 coupled neighbors, whereas the peak corresponding to the blue labeled protons actually has only 2 lobes because there is only 1 chemically non-equivalent coupled neighbor. So I can predict that I should see an NMR spectrum for this compound with a doublet at 1.1 and a septet or multiplet at 3.7 ppm because I know about the shielding characteristics and the effect that the chlorine has, and I know how each of the non-equivalent hydrogens should couple to one another. How about 1-chloropropane, a very similar molecule? Well, it's going to have a very different NMR spectrum. In the case of 1-chloropropane, simply by relocating the chlorine within the molecule, I've created a situation where there are now 3 different sets of hydrogens which will couple to one another differently. So notice that I've got 3 different sets of multiplets here, none of which look like those in the above spectrum. Take a look at those blue hydrogens there. In this case, I've got a sextet instead of a septet, and that's because there are 5 non-equivalent neighbors coupled to it. So, using what I know about shielding effects and magnetic coupling, I can predict that 1-chloropropane should have an NMR spectrum containing a triplet at about 0.8 parts per million, a sextet or multiplet at about 1.6 parts per million, and a triplet at about 3.3 parts per million.